Welcome everyone to this the last Applied AI launch talk of 2023. I see we still have a few people joining us here in the live audience. Welcome to you all, and also welcome to those of you joining us online. So the live streaming is made possible because we're collaborating with AI Denmark. We're also collaborating with the Pioneer Center for AI. So also a greeting to the Pioneer Center. I know that some people are sitting in there enjoying a live streaming as we speak. Today we have Michael Fuglsang from Force Technology, who's going to be talking to us about physical informed neural networks and how they can inform hybrid conditioning. And also we have Rasmus Sune-Ree, who's going to represent how we can use the test and experimentation facility for AI, which is going to be premiered early 2024. 2024 is just around the corner, and also means that we're starting a new round of Applied AI launch talks. So if while you're listening to these talks, you get inspired and you think, oh, I should be on those talks in the spring, or my colleague should, or oh, I wish we could hear from so-and-so, please do send me an email. You can scan the QR code on the screen with your phone, and it's going to send me an email to nominate someone that you'd like to hear from. So no end of year without also Christmas gifts. The New Year's gift is going to be for us, the nominations, but the Christmas gift could very likely be for you. If you want a dose of applied AI during your Christmas break, you can scan this QR code, and you can actually view all of the applied AI launch talks we've filmed so far on the website. So please make use of that. We're going to put it on at the end of the session today as well. So if you don't scan it right now, you can do it later. I'm about to welcome Michael Fuglsang to the stage. While he talks, you can type up questions in your notes, or you can put them in the chat if you're viewing online, and then we'll take 10 minutes of questions after his talk. The stage is yours, Michael.
Thank you. Yes, I'm going to tell you a little bit about how we are working with machine learning in hybrid testing, and we found a method to do so, which is called physical informed neural networks. That's me, Michael Fuglsang. I'm a mechanical engineer from DTU, but I've been working with AI and machine learning for the last 6 years, and now I'm heading a small team of robotics engineers, but also taking part of these projects, which is run within GTS. Oh, sorry. Screens are popping on and off in here, which is run within this GTS Institute, which is Technical Research Institute of Denmark. So we are running a project in hybrid testing, using some of our test facilities and trying to digitize the facilities and the results coming out, and see how we can help industry get use of that. Within Force, we have more than 400 different facilities, testing facilities, and have a lot of different courses and practices, and we are doing a lot of different projects with companies around Denmark, and we are doing a lot of research and development as well. So one of them is this hybrid testing and digital service, where we want to see how we can digitize and automate the process in the future, both infrastructure and asset and single project products. Yeah. And what I'm going to be talking about is within digital twins, because that's one of the end goal is to have a digital twin of every asset out there. So we're going to go around this product life cycle. So how we develop products and how we test it and can use that for monitoring, condition monitoring, why we want to do that. And then we are developing virtual sensors. And then I'll tell you a little bit more about physical informed neural network, also known as PINs, and how I see the future of condition monitoring based on this. So if we have like this circle of developing a product, you get some requirements, you do some field work, then you do some design. And in this design process is also normally a lot of simulations. It could be finite element simulation, see if the strength is good enough, if you use the correct amount of material. It could also be CFD simulation to see if your flow is correct. You end up doing some testing to make sure that your prototype meets with your design. You do the production, you have some quality to make sure that your production went as you planned. I talked about that last year. Then you have some deployment where it goes out into the field and is working for real life. You could have some input back and redo the whole circle. What is interesting for us in this context is the design, because in the design we have a lot of digital going on. We have a lot of simulation. We have that goes into the design. We have some testing where we actually get some results to make sure that our design meets what we expect. And that is what we want to use, actually, to do a setup that can tell something about if the asset is acting like we want it to do in real life when it's done. And why do we want to do that? We want to monitor our assets to make sure that we have the most optimal production. So we are not running it at sending in too much energy compared to what is coming out, and that also makes it more cost efficient. And then we also have a thing that calls predictive maintenance. Because normally when you run your car, you have service for every 20,000 kilometers. That's this preventive maintenance. You go change the oil. That means the number of failure is very low, but the cost could be very high. We want to find the optimum where the cost of doing these repairs are the minimum. So before something starts failing or the failure starts costing a lot of money, we want to find this optimum. And we can do that by applying a tons of sensors. So if we just have sensors everywhere, we get a lot of data. And having vibration sensors, flow sensors, and filling everything up with sensors could be very expensive, but could also interrupt our production. So if we have a pump facility to measure the flow in the tube, you need to put in a sensor that actually is acting with the flow. So we want to use our digital twin, our knowledge about how this system is working. We want to use that in order to get good results. So we can use the digital twin, and based on the simulation, if we measure the pressure and the rotational speed of the pump, then we can know something about what is going on in here from our physical model. And we actually did that. We tried to do kind of drag and drop system where you can drop your pipeline system and you can apply a pump. This is a small setup. And then you can apply some sensors saying we know the rotational speed, we know the pressure before the pump, after the pump. We know something about these pipes from our simulations. And we have some surfaces in between these that are important to know the velocity profile and the pressure and different temperatures and things like that. And what we want to do is we want to run this and see that we actually get the correct output. So if we run this, we have the pressure dropping, we have the RPM dropping on the pump, and then the lower graph, we have the dotted line is the virtual sensor, and the black line is the real flow. So we see that there's actually some points in the low speed flow where our digital model is not correct. It's not giving the right results. So we want to do something about this, and that's where physical neural networks can play an important role. Because if you have no data, you'll do numerical calculations just based on the physics, and you will set it up with a tons of parameters, and you'll not describe it fully, but doing it with a lot of data. If you just had the pump running for a long time, collecting all the data and then doing a normal machine learning model, we wouldn't need the physics, but we could do it just data driven. But in here, in between, we can do a neural network that is based on the physics. And how it works is that we have the neural network that we train and compare with the data, but then our loss function in the end of the neural network is our physical description of the problem. So going back to the pump, run it, calibrate it, put in the training data, the data points from running the pump system, and reapplying that to the model. That will help us make the result more similar to what we see in real life, without the need of running it at every RPM and every pressure difference. So one of the advantages with applying the physics is that the function actually know what is going on. So if we have normal neural network, we have a bunch of points, which is kind of our trajectory for a cannonball. A normal neural network will try to minimize the loss function by finding the function that goes through all the points and ending up actually finding a solution where the ball never hits the ground. If we apply the physics to the loss function and we have gravity in here, we actually see that it won't apply all the function to be close to all the points, but it will end back in the ground. And the gray line in the back is actually our real trajectory from the physics sense. So we will end up with something that is actually based on the data points that we have, comes out with a result that is quite similar to what we will see in real life. And that makes it possible to do complex cases as well. So if we have a complex geometry, we want to see the flow through this, we can set it up and create the domain, solve the Navier-Stokes, or set up the Navier-Stokes boundary conditions for all the spots in the domain. So here, each dot is not connected, it's just nodes floating in the air. And then we have this red surface in here. It's an integral surface where we have some data for what is going on. So we will solve the numerical Navier-Stokes, but at our solution we will satisfy what we have measured in here, and we will come up with a faster way of solving the flow. So what is the advantage of PINs, physical informed neural networks, is that we can, based on a small amount of data and a lot of physics, we can actually apply the power of machine learning. And we can solve with data. We can solve these partial differential equations for more than one problem. So we can do transfer learning from, for instance, heat transfer and flow. So we can have those two combined in the same domain. And we can have efficient models that are running real time with sensor inputs. So the future of these pins would be that we will have virtual models that is actually based on design and test results from the early stage of the product development. And we will be able to calibrate these with the full system and have models running. And we can have it running in live sensor with real-time virtual models running besides it, but also be able in the digital twin way where you can say, what if I do this change to my system, what will happen? And then we can use machine learning anomaly detection to see if our system is running as we intended. And of course, we can apply predictive maintenance.
Thank you so much for an excellent talk. Let's see if we have some questions in the audience.
I was wondering, thank you for the presentation, it was really nice. I was wondering whether when you are working with some predictive models, that they sometimes become insufficient, even though you are applying both AI and some physics on top of it.
Become insufficient?
Yeah, like where they end up not being accurate, even though you spent the tools.
That's the hope of this. We have tried to do the like just machine learning way, just the normal neural network, and we end up with something that is not. It's diverging in another way than the physics will allow it to, and by pushing it with the physics, it makes it more robust, and you can weight how much you want to trust your physics and how much you want to trust your data. So if it's not diverging towards the actual result you want, then you want to go back and look at how you're weighing the different sensor inputs. Because this is also, as you saw with the Cannonball, it will also diverge on input noise. So you will actually, if you put more into your physics than your data points, then you will have it coming out with results that are more closer to your physics than your sensors. But you could also weigh the other way and have it trusting the points, your data points more. So it depends on your data set.
Okay. So my background is in biology, so we always have outliers and data that cannot be used to give a perfect picture.
Yeah.
That's the reason why I'm asking.
So in what I've been looking at at some points where you have sensor noise. So that will be the same. You have some outliers that you don't want your model actually to fit to, but because if you bound it more on the physics behind, it will pull it away and leave those outliers. So it won't try to fit something through a data point that is an outlier.
Okay. Thanks.
Any additional questions? We have some here.
Thank you very much, Mikael. Really exciting also to see what the digital twin will bring in the future. So now you're talking about how to use data from a production side where it's very easy to go and set up sensors and also to test whether the data is correct. But if we're looking into production sites that are really far away and not easy to get to, for instance, like offshore wind turbine parks, how far are we for having these digital twins out there and also to do predictive maintenance? So I know it's quite expensive to go out there, not an easy task either. So how far are we to use digital twin for that purpose?
That's a good question. I actually don't know how far we are because the turbines are a bit of a complicated system, and the first thing is to identify what type of sensors you would like to have the full model. So I don't know where we are in terms of doing that, but the idea is that you could you can calibrate your model based on tests you do in the lab, and then look at the sensor input for a given period of time from the sensor that is based on in the field to do a digital twin that's individual for each turbine. I know the digital twins they have done now, which is based on just simulations. You will have like the perfect turbine that will represent all the turbines in the park. You'll have one model for all the turbines in the park, and that will be the ideal turbine. And it goes in production that nothing is ideal as it is in your CAD model. There's always something which is not according to tolerance, or is with a tolerance, but tolerances are different directions, and then you can't say, is it the sensor that is doing something wrong, or it's just the mechanics of the turbine. So hopefully in the future, but I can't say when, we will have something that is an individual digital twin for every turbine.
Any more questions in the room? We have one over here.
Thank you for the talk. It was very fun to see the combination of the physical limitations and the AI together in one. I have a question regarding how you choose which physical limitations and physical laws to apply to the AI to get the best result. Because obviously there's a lot of different physics that go into the flows of these things.
Yeah, that you need to have that as your description for the simulation that you're doing. So if you're doing something which is simple, you will apply like the simple form of Navier-Stokes for flow. But if you're doing something more complex where you know that you're going to have turbulent flow, you need to do that as well. But that's one of the great thing about these tools is that as long as you just have a partial differential equation that will be solvable for your problem, then you can apply that and you can combine it with the data. So even though if you actually underperform on the physics, you'll just need more data.
Thanks.
So does that mean that you could also add in quotients for vibrations or other things that could influence the time of maintenance?
Yeah.
Yeah.
So you can add all the different domains in your model and then do transfer learning in between and then have a full system.
Mm-hmm. Excellent. Do we have more questions? Yeah, we have one down here.
Yeah, thanks for the talk. And my question is that this physics-informed loss function seems to be more complex than the standard one because you need to apply those equations. So how does it affect the training time? Is it make much longer or maybe actually make it shorter since you need less data?
It makes it shorter in the machine learning way because you need less data. But as we have people working solely with fluid dynamics and aerodynamics, they kind of make fun of the machine learning people because we want to solve their problems by using this. And we are getting to them for asking how to set everything up because you're actually setting your machine learning up as if it was a CFD solver. Okay. So you have, like they say, in all the literature that's out there, it's never the CFD people that do pins on CFD problem. But you could actually, with CFD, with Navier-Stokes, you can solve the same problems, but it takes longer doing it as a pin. But once you put in this, like this surface, some points along the way say you need to solve according to this, then it speeds up the process. So what we are doing right now is we are setting up our model, see that it runs, then we get CFD data to enter into it and have it accelerate. And one of the things we're going to do next year is we are going to set up, we have a physical facility in Lyngby, where we're going to set up the test to do CFD pins with CFD data, and then compare those two. How much does it actually cost, and how much do you need to inform your network to balance it out, and then go in the lab and see who is get the closest to a real product or a real flow in the lab.
Thanks.
Do we have more questions in the room or any online? So I was curious, do you have any calculations on what you save in terms of cost spending and when you apply this kind of methodology?
Not yet.
So that's for next year as well?
That's for next year as well. Like the physical informed neural networks is something that is come up now. 2017 is like the first description of it, so it's only 5 years old as a framework, and that's why we are like frontiers of trying to pull it into the industry and see how we can benefit from it. So we don't have any numbers, but we are because we are on an early stage.
You'll get an invitation to come back and tell more about the numbers then.
Yeah.
Wonderful. Let's give him a hand. And the next speaker on the stage is going to be Rasmus Reh from the Testing and Experimentation Facility.
Yes, thank you. So this is completely different, yet very much the same. So this is sort of stepping up from one test to actually sort of have a test platform, and it's so what I'm going to talk about is a project we call, or facility we call SITCOM AI, which is a test and experimentation facility for cities and communities. So it's an EU initiative. Yes. So who am I? I am sitting in DCU Compute in the dynamical system department or group, and we have a subgroup called Connecting Communities. So we actually sort of based here. We have also science behind math of how the digital twins and data can work together across different sectors. So my role is very much the translator of the EU system to actually sort of be able to fit it in to where the problems are and needs to be solved. So what is a TEF? So really it's a TEF, it's an instrument to accelerate uptake of AI. So when you have or someone else have a product, AI-based product, that is almost ready to be put into action, then you can test it, and we can the customer can see what does it actually do. Is it compliant with all the regulation that perhaps a city would need to have sort of insurance of? Does it actually give the sort of effect that it's promoting? So it's very much around the first sale of a new technology. So building trust and sort of extend that trust to the customer so they can come and buy. So having a test in the TEF is actually sort of supposed to be at least thought to be a good step forward, and this is what we try to work very hard to actually sort of achieve. So we are sort of a direct part of the Digital Europe program, so the EU Commission's efforts to actually sort of accelerate. And there's a lot of things going on, but really what it is about to accelerate European technology, not only to Europe, but actually to the rest of the world. And then we have some some European ways of doing things. So we have rights, and we have protection, and we have sort of that. And that sort of friction that stalls the processes you need to sort of comply and know a lot and then you have some accelerators. So we are thought to be the accelerator. So we have these dual perspectives, and it's the digital comes in that this is sort of a cross sector. So we actually try to work on digital tools across all sectors. Yes. So in more practice, I think what is important on this one, if you look to the right, there's actually legislation at the end. So any product that goes into a city needs to be compliant with regulation. And there's a lot of regulation coming. So if you are an innovator, you should actually look at what regulation will hit. But one of the things, one of the new acts is the Interoperable Act, where cities, when they buy stuff more than 1 million euros, then they have to comply. So that means, and perhaps it's 2 million, it's not fixed yet. But anyway, when they buy big stuff, they need to comply with interoperability perspectives, or sort of regulations. And that sort of will kick in and also affect all subcontractors. So actually sort of a new set of standards are coming. And then there's the data economy built around. So there's a data space where you have sort of how can you actually exchange data, how can you use data, how can you buy data. So the technical and governance element, and then we have sort of the local digital twins and how can models actually work together, and so on. The TEF, the Sitcom AI, is then the testing element, sort of just before market to put it out. Yes, also there's some ethics coming, European Digital Infrastructure Consortia, which sort of package it all, and the cities can just go in and say, this is how we do it. So what is a TEF? For who should use a TEF? So one of the elements we are looking at, if you're an investor, you come say, is this actually sort of this solution or this company, should I invest in it? Do they actually keep their promises, and can we trust the solutions? So one of the talks I had with one of these sort of AI innovators who was very interested in this, because as a woman, she also always felt that she was 20% less lying than anyone else. So actually being able to document this is the effect of a solution would be sort of a factual way for her, but also for investors to actually see, can we expect a market for that. For buyers, part of the procurement, so when you buy stuff, the city wants to buy an AI solution. Have it tested before. What are the transparency, the legal, all that, so they know. So that's also a way to use a TEF. And then I think the innovators, that is probably most of you here, how can you actually use a TEF to bring your service or your solutions to the market? So if we look a little bit more on that element, so we start from the right, you end up with a sort of a stamp, say this has actually been tested, it's compliant, it's working, and so on. Then before that, we have different types of tests that we put up in a catalog. So you can have it tested for cybersecurity. Does it actually work? Is it secured? And if you have energy solutions, you have different speed limits, sort of speed elements you need to comply to, and so on. So you could have some specifications of a buyer that you need to fulfill. It can also be in industry where sort of you have different and more sort of more specific sort of demands, so you can actually comply to that. So this is sort of the testing element, but you can also use it more in the experimentation element. So what we bring is also that you, as an innovator, get what is the market you're entering. So if you have to comply to certain standards, then when you start your development, you actually start knowing what you need, what target you need to know. So it's a technical, it's a legal, but it's very much also a documentation element in that. So that is sort of workflow element that also comes with this platform. Yes, so who are we? We are DTU Compute, so we're the coordinators of that for the whole of Europe. And then we have a sort of a Nordic setup, which I focus on today. So we have Webull Denmark, Aarhus, sort of a TI in this. And Center Denmark for energy and so on. So there's a lot of partners. But then we also have TEF-DK, which is really a Danish association, which is open for all. So anyone that have a test they would like to sell in this market, they can actually come through TEF-DK. So Mikael's PIN can actually enter and say, I would like to have extend this testing to not only to industry, but also to others that can use it. So they can come to Mikael and have it tested. So Force is actually part of TEF-DK and is actually a co-chair. So it's just to say that we have an open structure where people can enter also from later on. We also have 2021 AI that sort of have this documentation and governance element to it. Yes, so how does it look? So one of the things is Aarhus. City of Aarhus is probably sort of a weird test environment that you would think. But this is actually where you can go and test your product. So if you remember the robot first and the kids lying around, if you would like to have a park service where you use robots to go collect waste, then you need security so children are not going up to it and have their fingers cut off because they put it in the wrong places. So latency, security, all that kind of security that could go into it. And this is one of the things where you can go and test it in Aarhus. So they have an area around the harbor side. And then you can actually sort of test how fast does it comply? Is it secure? And then you have different kinds of tests. So we imagined something of Force as a laboratory where you can test the first prototypes, and then when it comes just before market, then you can actually go in real world environments and have it tested before. So this is AI and robotics and so on. So we also have other places. This is actually Milan. So the old Olympic city is now being transformed into a living lab, really. And sort of any service on infrastructure, on facility management, of biodiversity in parks and stuff. Then they have sensors up. You can test your ground, but you can also come test your solutions. But you can also come and use the data. So you can actually sort of use the data to make solutions first. And there's a sort of variety of data sets where you can actually add, and you have that for all of the test sites. So this is very much the TEF sort of providing data, providing twins, providing test opportunities in order for AI solutions developed in Europe to come to a market in Europe, but actually sort of extending out to global. So that's the perspective of a TEF. Thank you very much.
Thank you so much, Osmus. Let's see if we have some questions. Looks like we got one over here.
So thank you very much for the presentation. I was wondering, the focus on cities and urban environments, it seems like the methodology could be applied in many different contexts. So are they, and is it, are they different? And if so, are the different initiatives connected?
Yes. So there are actually 4 TEFs. So one in health, one in agri-food, and one in industry. So those are the 4, and there's also one in sort of semiconductors, kind of. And we work very closely together. We have same kind of setup. But in Denmark we have the smart city elements, and then we also have the manufacturing. There's also Force is actually part of both of these sort of TEFs. The health. So the 3 others are actually sort of very domain specific. So the health is really what's going on in the hospital. The agri-food is really what's going on a field or a greenhouse, and the industry is what's going on in the factory. So ours is then what is actually sort of horizontally connected. So as soon as you have any technology that is close to people on a place, then it's us. But then the other ones are more specific in the other elements, and that's sort of where we are in the TEFs. There were a lot of TEFs sort of scheduled, but I think they're sort of merging it more into these 4.
More questions? I have one. So I'm curious about the technology readiness of the startups or the SMVs that connect with you. What level should they be at, and what does it cost to work with TEF?
So we are designed to be 6 to 8. So 9 is market, 8 is then just before market, and then 6 is when you have a working lab prototype, something like that. And these TRLs are often somewhat difficult to look at, sort of because you always have different elements where you have different readiness levels. So you can have an AI component that is almost ready for market, all ready for market, that you can have tested. But then you can have a physical element that is not necessarily ready to go. So the robot element, you have a robot. The physics, mechanics of it is not fully yet in TRL 6 to 8, but your AI element is ready for market. Then you can have the AI tested.
So you can get started on whatever is ready first.
So you can use it also as a way to pass gates in your development process. So if you have AI, this is phase 1, and you have that ready, and you need to pass and document your results and go for next funding round or next soft money or something, then you can have it tested, documented your effect, and go on. And then have it as a different, the mechanics or whatever else as a separate track.
Mm-hmm. And you've given an example of the Aarhus test facility and the Milan, but how about the AI part of it, like the non-physical elements? Can you elaborate a little bit on that aspect?
Yes, it is just always so difficult to show digital infrastructure. But we at DTU Compute, we test algorithms. We test them for leakage. We test them for can you actually sort of are the cyber secure and so on. So we also test we can test algorithms also. Yeah, it's difficult to show how to do that, but it's really a virtual lab connected to it.
Okay.
Yeah.
Cool.
Thank you very much. We have 2 questions online. I think I will combine both of them. One ask about how does this work in practice, and also what does it cost? I mean, you have this blue label certificate by the end. So, as a company, how do you get access to this, and how much do you pay? And then also a person asked about whether it's only smart city, which goes for the TEF that you're running, but I guess how can you get access to the other TEFs around Europe?
Yes, so I think in essence, if we are officially starting open for business 1st of 1st, so end of when the new year begins. So some of these procedures are not necessarily super sort of in oil yet. In Denmark, TFDK is hosted by Danish industry. So if you contact them, they sort of take care of how to get to it. If you have contact Force, then they are also sort of able to say you should actually go through the TEF. So we try to make it as smooth operating as possible, but we're not fully up and running yet. So if you contact us, then we'll take care of it. And that goes also for the sort of European and the health and the agri-food and the sort of the industry elements. The health main office is in Berlin, so that's the Charité, and the agri-food is actually in Italy. And then you have sort of the AI Matters, which is the industry. They are in France. That's the headquarters, but AI Matters also have a technical institute in Odense as sort of the Danish node. So yeah, contact us, and then we will make sure that you be sent in the right direction. And then later on, will there be sort of more an entrance? Yeah.
Do we have more questions? We do.
The price was also a question.
The price. So depending on, we are not able to give you money in the sense. We cannot sort of pay part of your development expenses. But we can give you free or services at half price. So if you would go to someone to have a test, you can have it at a reduced rate. And this is, as always, applicable to if you are a small or medium-sized company. So if you are less than 250 employees, you have a market cap, I think it's 50 million or whatever, quite big in Danish sort of context, then we are able to support with sort of services or tests at reduced rate, around 50% in average. But we also have extra funds. Yeah. It's not fully up yet because there's also legal stuff in this, so that's why I'm sort of weavering a little bit.
Thank you so much. I'm sorry to ask something more about this, but are there any requirements? Couldn't everybody just apply for it, or what are the actual requirements to get that 50% off the testing facilities?
Yes, and this is a work in progress. So I think at the moment we have a sort of a wider funnel, and then demands and sort of specifications needs will be sort of tightened when more comes in. But in essence, you need to show that you are state of the art. So and that you can do by having a patent or sort of something where you have universities saying this is not done before, this is smart. So as I said, we are not fully up and running yet, so there's a lot of these procedures, but it's not everyone. If you have a solution that is not state-of-the-art, then the European Digital Innovation Hubs, and they have actually sort of many of the same services, but on a more broad sense. So if you have things you would like to have tested or that kind where it's not necessarily a super novel technology, then you can use those kinds. But again, come to us and we will direct you also to the EDIs.
Thank you.
Do we have more questions in-house or out-of-house? Otherwise, I have a follow-up one. I think it's so exciting that we have something in Europe that's not like the regulatory guard dog, which we've been known to be, as opposed to China or the US. Actually, we have something here that seeks to accelerate the innovation and build trustworthy AI, because oftentimes people's fears or hopes are unrealistic, and this actually backs it with some solid knowledge. So that's super exciting. You also mentioned an example of a female entrepreneur. So it could potentially help with that knowledge to prevent some of the biases that people see in this process of either fearing or hoping too much. Can you elaborate a little bit on the transparency that the TEF is going to hopefully add?
So this is not sort of an intended part of the TEF, but it's quite obvious to us that when you create a sort of a level playing field, a lot of these other elements tend to disappear. So if you are able to document that your solution is 20% more efficient than the rest of the market, then it might be easier also for minorities or women or what else, where you have human factors that would perhaps sort of inhibit the same kind of take-up. So the test results will be a level playing field for everyone, and this is also where we see sort of an interest for the investors, because it can be very difficult to actually see through what new technologies work and what do not. So we will support what works, and no matter actually who is who, so to speak.
Yeah. So another question could be around these use case scenarios, right? Whenever you test a new technology, there's certain, it's supposed to be used like this scenario. And if it's used in a different way, it might harm the user in some sort of way. How do you define those different scenarios that you test? Because what we know from human-computer interaction is that sometimes users are so ingenious in the ways that they use a system that they exceed any expectations that the designers and the engineers had.
Yeah. So one way to start that answer is that you probably cannot make sure that technology is not applied in a bad way if people really want to. But also when you have regulation, this is the framework of the regulation. You have a sort of an area where the regulation works, and when we test, then that is also what we test inside. So if you are testing robots in a park, then you need certain elements in order to make sure that when it's public and you have people around, then there's a limitation on speed, there's a limitation on distance to people, and that. So, but if you change the parameters, then you need a new test. So if it's a new regulation you enter into when you transfer your technology, then you should probably have another test in that regulation to make sure that it's compliant with that regulation as well.
Yeah. So it's context dependent, kind of like autonomous vehicles that work well in cities with perpendicular roads and not so much in old cities.
Yeah. I think we are caught in the same quagmire as everyone else in that matter.
Yeah. Well, thank you so much. And hopefully we can get an update when you're up and running and hear more about the cases that go through the TEF. So I promise to put these slides up again at the end of the session today, and that's where we're about to arrive. If you have suggestions for talks you want to hear in 2024, then you can scan this QR code. It's going to open an email to me, and I'll see if I can make your wishes come true. There's also another QR code. I'm just going to let this one be up there for a little bit. Otherwise, you can find me on Skylab's website. And I see a person scanning, so I'm just gonna wait for a second. The other QR code is in case you need an extra dose of applied AI during your Christmas holidays, who knows? Then you can view all of the talks that we've had so far. The 2 from today are not going to be up there yet, but you can view all the other ones that we've filmed and learn a lot. We always do in this setting. And I think that's all from us for today. Thank you so much for joining.